Electric potential. So for the electric field in lecture 1, right, E was equal to force per unit charge. And we found that it was more useful to express a particle's mass scaled acceleration on a per unit charge basis, right? This is that per unit charge, so it's some force per unit charge. Well, this abstraction cost that we paid earlier can pay off now. It provides us a quantity that describes the electric field from a charged body, irrespective of any charge that would experience it if we were to drop it in the field. So in other words, we have something that causes an electric field, right? And we want to describe that field that a thing causes, say a point charge, right? It's going to cause a field around it radially out. We want to describe that not with reference to some other charge that would experience it, but just on its own. And so that's where that concept of a unit charge came into play, right? And so if something is per unit charge, then it's just 1 coulomb, and so it's just this quantity E that is valid for for any unit charge. So if you then go and apply some charge, say some charge, stuff's in there, then you know how much it scales by how large that charge is. So in other words, if we were to drop some point charge like plus 5 times Q naught, right, equal to 5 coulombs, so this is some positive charge, you know that the force that it would experience is equal to 5 times E, right, or 5, yeah. So this type of thinking lends itself nicely to potential energy as well. And if, as we just learned, the potential energy of a positively charged particle, so like plus Q1, in the presence of another positively charged particle, plus Q2, is given by what we wrote before, but this time just both are positive. Equal to K Q1 times Q2 divided by R, then we might consider the exact same concept of what is the electric potential energy on a per unit charge basis, right? So we have Q1 causing the charge, or causing the electric field, and Q2 in the presence of that field, right? 1 and 2 chosen arbitrarily there, but one's causing it, the other one's experiencing it, depending on which perspective you care about. And you might just want to describe the field of one of them or the other, irrespective of another charge that's present, right? So equally two gravitationally attractive bodies or something, right? You and the Earth here, maybe, right? Right? And so you might be M1 and the Earth might be M2, right? But you might want a way to describe that interaction without you having to be constantly part of it, right? And so that's what we had done. That's actually, what G turned out to be. And so for this case, we are going to just simply divide this electric potential energy by unit charge. So we're going to call this capital V for potential. So U electric divided by a unit charge. So we're going to pretend that one of these is like a unit charge, right? We'll say it's Q2 maybe. And so what that leaves us with is K times the charge that's causing the field divided by R, right? So we've just divided a charge out of it, and we've left ourselves with the charge that we cared about. right? Both could still exist if there were actually two charges, right? Like up here, right? There's actually two charges. You could describe the potential respective of one or the other. But this gives us electric potential energy of a point charge, in this case, right? Irrespective of any other charge that would obtain the electric potential energy if we were to drop it in the field. So we call this simply potential, or V, right? So this is potential with a capital V. And it turns out that this quantity in particular is incredibly useful for all things electricity. And you might be familiar with what the term that we use for the difference in potential, so difference in potential is equal to delta V, or V2 minus V1, right? Potential at two different points, not potential energy, potential, this per unit charge thing. We call that voltage, which I'm sure you've heard before. So yeah, voltage of like a battery is just the difference in potential, or in other words, the difference in electrical potential energy per unit charge, or the work done by the electric force when a unit charge moves from point A to point B. So a difference in energies being equal to the work done is familiar to us from kinetic energy, gravitational potential energy, and elastic potential energy, and they all take the same form of description, which we've talked about earlier in this lecture, with a difference in energy terms being equal to the work done on a body. So for electric potential, which is, for electric potential energy, not potential, going back to electric potential energy, the work due to this difference in an electric potential energy would be equal to K times Q1, Q2 over R1 minus K, Q1, Q2 over R2. We just covered that. For potential then, right, so this is the, electric potential energy, here we'll say U elect is equal to K, Q1, Q2 over R. For potential then, we have the work due to electricity on a per unit charge basis. So work per unit charge, Q naught. And that's equal to V1 minus V2, 1 minus 2 for the same concept as we discussed before, which would be U elect 1 per unit charge minus U elect 2 per unit charge, or, of course, its final form, which we just described up top, of K Q over R1 minus K Q over R2, right? So we can write difference in potential is equal to, of a point charge, KQ over R1 minus KQ over R2. That'd be probably the most useful and concise way to describe, but those are all true, all those things. So remember that these expressions are specifically for a point charge, but the same concept actually applies to collections of point charges, continuous charge distributions, like charged surfaces and charged volumes. So it applies in general. So since the joule is the unit of work per unit, the unit of work and energy, right? So the joule, potential has units of work per charge, and so joule per coulomb. That would be the units of work, of potential, I'm sorry. And so, let's jump right in and try to describe the situation that we had before. this one here with potential, right? All right, so let me go grab this guy here, if it will let me. Cool. All right. So, oppositely charged parallel plates. We were just looking at this, right? Top one's positive, bottom one's negative. Electric field pointing straight down. Have some displacement along the y-axis. And it asks us to find the potential at any height y between the two oppositely charged parallel plates. And so, if the potential is, so V as a function of y, is simply the electric potential energy as a function of y divided by Q naught, and we're actually, talking about a Q naught here, then this is simply Q naught E times y, right? That would be the electric potential energy for this Q naught charge, but it's on a per unit charge basis. And so talking about a unit charge, per unit charge basis, so the potential as a function of y is simply equal to E times y, the electric field times how high it is off of the quote-unquote ground, right? And so naturally potential decreases as we move in the direction of the electric field from the upper to the lower plate. And you can plug things in and demonstrate for yourself. But our result shows that V at the bottom, right, V at y equals 0 is equal to 0. There's 0 potential down there at the origin, right? Because you plug in 0, E times y, that'd be E times 0. So no matter what the electric field is, down there at the bottom, there's 0 potential. And at any point up here, like say D, right, you would plug that in and you would get the appropriate potential. All right, so maybe that's too simple to actually have any kind of aha moment, but hopefully it shows how natural potential can be when you're talking about fields and unit charges, right? So these unit charges just cancel right out, and you get a quantity just in terms of the field and whatever distance the thing would be away from wherever you define 0 potential. All right, so now let's do a little bit of a more involved one. So here we go. So here we don't just have one unit charge. We have 3 charges that are not unit charges. We have 3 kind of actual charges, so to speak. So 3 point charges. We're going to consider them initially infinitely far apart. The reason for this is because if they're infinitely far apart, then that is at 0 potential, right? Then, so because they're infinitely far away, right? So infinity, that's a, conceptually overwhelmingly large distance away from each other, and so they are far out of range to have any interaction. They're not in each other's fields, right? And so the question is, what is the potential of this arrangement here? So if we have a charge Q1 of 5 microcoulombs, positive 5 microcoulombs, Q2 of positive 6 microcoulombs, and charge Q3 to equal to negative 2 microcoulombs, if it starts out at 0 potential energy, each of them, or 0 potential, each of them infinitely far apart, and you bring them together to make this equilateral triangle of ½ meter between each of them, then what potential is it sitting at? So this might not make too much sense right now, like these words, you understand them individually, but what is this situation? What does this actually mean? So It is a little bit abstract, but I want you to kind of picture that you're pushing a box up a hill or lifting a box up, right? So they're starting off, quote unquote, on the ground, like infinitely far apart from each other. And you're pushing them together such that you're creating some potential. So it's analogous to a box that starts on the ground and you're lifting it up some amount, right? The interesting thing is not all of them are positives. They're not all repelling each other, right? So Q3 is negative, and it's actually a little bit attracted to Q1 and Q2. So it's not all, you know, it's not all uphill, in other words. And so it kind of challenges you to think of this concept of like potential energy and things rolling, you know, from uphill to downhill, higher potential to lower potential. It's a really complex kind of a arrangement here where some of it is uphill and others are downhill, right? So to bring Q2 and Q1 together, it would be like pushing something uphill, right? You're bringing it higher potential, because if you brought them together half a meter apart and then you just let go, they would move away from each other. They repel each other. But Q3 here is rather attracted to each of these other positive charges. And so to bring it into this scenario is actually moving it downhill, right? Because it's attracted, and so it wants to move in the direction that you've just moved it. And so there's three moving parts here, and to get them from infinitely far away to close together in this equilateral triangle, some of them have moved uphill, others have moved downhill, and we're going to calculate the total, you can think of it as elevation change, right, of all these things, the total potential that is that these are sitting at when they're in this arrangement. Hopefully that makes some sense. So to move one from infinitely far away into its position, right, so literally talking about charge 1 here, from infinitely far away to its position here, it actually hasn't changed in potential at all. Even though it has changed position, the other two are still infinitely far away, right? So even though it's moved from infinity to closer to this, you know, wherever this center triangle, center of the universe, as far as these three particles are concerned, these other two are still infinitely far away. And so there's actually no interaction still between this one and this positive Q1 sitting in that new position. They are still infinitely far away, right? So so the potential of bringing the first one in is actually still 0, right? So let me pick up with where I wrote my notes here. All right. So let's see, how do I want to write this? So electric potential energy of 1, I'll write U elect 1 is equal to its charge, Q1, times the potential of each of the other 2, right? So the potential of 2 plus the potential of 3, but they're infinitely far apart, right? So this potential being R there, right? So if R is infinity in the denominator there, then the potential is 0. And so these are both 0. And so the electric potential energy of charge 1 sitting in its new spot at the top of the triangle is still 0 joules. Okay? Meaning that if you let go of it, it wouldn't go anywhere. It doesn't really care, because the other two are infinitely far apart. They're not interacting. It's not in the field of anything else. It's just now sitting a little bit from, you know, I don't know, you can think of it as double infinity away to now infinity away. But as you move the next one close, and the order doesn't matter. You can verify for yourself. We could start with 3, then go 2, and then 1, but I'll just do 1, 2, 3. So as we bring the second one close to its new position as the bottom left point on the triangle, now these two charges are within some non-infinite distance apart. They're a ½ meter apart, and so there will be some potential here. And so now, once charge 1 is in place, the potential that it creates at that corner here, the bottom left corner, is not 0. And so we can calculate the potential at this position here. What do I want to use? The potential at this position here due to charge 1 now being at the top of the triangle. So V1 is equal to KQ1 divided by R, R being this distance here, right? ½ meter. And they're all the same, equilateral triangle. All right. And that is equal to, we know what K is, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, times the charge Q1, which is 5 times 10 to the -6, because microcoulombs, and then divided by ½ meter. And that's going to be equal to a positive 9.0 times 10 to the 4th volts. All right, joule per coulomb. So therefore, when this charge Q2 is then placed at that second corner of the triangle, the electric potential energy, so charge Q2, the electric potential energy 2 is equal to charge Q2 times the potential at that spot from charge 1, right? So that would be Q2 times K Q1 over R. And we know what that is, right? That's just this guy. And so we have Q2 being positive 6 microcoulombs times our last calculation of V1, so 9.0 times 10 to the 4th volts. And you get that the electric potential energy of Q2, once it's in that spot, is equal to a positive 0.54 joules. All right, so now thinking about that third charge moving in here from infinity to this spot here, we want to calculate the potential at that point. And now the potential at that point is altered by or affected by both Q1 and Q2's presence nearby. So the potential at that spot, we can say is equal to V1 plus V2, right, at that spot specifically. And they make it easy because it's an equilateral triangle, but K Q1 over R plus K Q2 over R, right? So it's the same R. In the first one, specifically though, this R here is talking about this R. So the distance from Q1 to that point that we're trying to calculate the potential at. And then the next one, this R, is talking about that R at the bottom of the triangle. Distance from Q2 to the point at which we're trying to calculate the potential at. All right. And so we know what both of those quantities are, right? You have to be careful to plug in the appropriate charge. Distance in this case is the same, but you should get a positive 2.0 times 10 to the 5th volts. All right. And so therefore, the electric potential energy at point 3 or of point of charge 3, right, is equal to Q3, the quantity of its charge, times the potential 1 plus 2. So these are per charge basis quantities, and then we're now inserting what the charge actually is, multiplying it by what the charge actually is. Right? So the potential due to charge 1 and charge 2 being there. And so this would be Q3 times K Q1 over R plus Q3 times K Q2 over R. Yeah? Just distributing the Q3. And that one is going to be equal to a negative 0.40 joules. Why negative? Well, because that's the charge that was negative, and so actually it enjoys being in that spot. It prefers being there instead of infinitely far away. I mean, it's attracted to these positive charges. So you've actually taken Q3 and rolled it downhill to arrive at its spot at the bottom right of this triangle. The other two, not as much relative to each other, but Q3, yes. And so the total potential energy of this whole equilateral group can be added up, can be calculated by adding up the electric potential energy of each, right? So U total is equal to U elect 1 plus U elect. It's getting kind of annoying to write elect so many times. 3. And so that is 0 joules plus 0.54 joules, and then minus 0.40 joules. And if you add all that up, you should get a positive 0.14 joules. U total. And in fact, since there is no other form of potential energy, we don't actually even need to specify electric, but that is what it's due to. All right, so what I would like for you to do is either pause now and do it, or after the lecture at your own time, do that same thing in a different order, any other order. So instead of doing Q1, Q2, Q3, you could do Q3, Q2, Q1, or Q3, Q1, Q2, Q2, Q3, you know. So do it in a different order, and verify that you actually get the same answer, right? Which makes sense, right? So it doesn't really matter which came first, it just matters, you know, where they end up in this electric potential quote-unquote hill, right? So they all end up in their final elevations, so to speak, and it doesn't really matter which one rolled up or down first. All right, lastly, we're going to talk about capacitance in the next section.